It's a pleasure to join you today and to be able to share some of the work that's been recently recognized. My work focuses on the center of the galaxy um, and on using new techniques for obtaining high-resolution imaging through the technique of adaptive optics. And this has enabled us to discover a supermassive black hole at the center of the galaxy. Now, this is work that's been going on for almost more than 25 years, actually, but started off when I first joined the faculty at UCLA with a relatively small team. So I really want to give a tremendous amount of credit to Eric Becklin and Mark Morris, who are shown here on the left, who have been my collaborators throughout this whole pursuit. And then on the right, shows my very first graduate student, Beth Klein. Over time, this is taken very early on, this photo, and at a time when this proposal was first proposed, it was actually turned down, which was an interesting moment in terms of the research. I had joined the faculty very excited about using the Keck telescope, which is the largest telescope in the world, and advancing new techniques in order to do this project. And so it was an interesting start to have it turned down, but it really reflects at the time, we were really trying something that hadn't been tried before. Today, we're a much larger team, and we've not only get a lot of telescope time, but we've become a project that provides a tremendous amount of leadership for the development of high-resolution imaging technology for large ground-based telescopes. So not only Keck, which is shown in the background, but also the future 30-meter telescope, which is an even more ambitious project. In this team, I want to highlight on the far left, Jessica Liu, and just to my right, Tuan Do. These are two individuals who have been with the project for more than a decade now. They began as graduate students and are now their own faculty in their own right, with their own students and postdocs who provide a tremendous amount of scientific support and lead pieces of this project. So there are two big picture perspectives on why this experiment is interesting to do. From a physics perspective, the questions are, do supermassive black holes exist in the universe? And can we use these measurements today to test our ideas of how gravity works? And the reason this is so important to the field is that black holes really represent the breakdown of our understanding of physics. They represent our inability today to bring together two fundamental fields in physics: the field of general relativity, which is the study of things with very massive objects, and of course what Einstein is so famous for, and then the field of quantum mechanics, which is the study of things that are very small. And today we don't understand how to bring these two fields together. And we believe that black holes, which are both very small, in fact, they're infinitesimally small from the point of view of our theory, and general relativity. All right. So from a physics perspective, that's why we want to do what we're doing. From an astrophysics or an astronomy perspective, we'd like to pursue understanding supermassive black holes in terms of understanding the role that they play in the formation and evolution of galaxies. At the time that this study was initiated, we did not really understand the relationship between supermassive black holes and galaxies. And in fact, at the time, there was a question of which came first, the black hole or their host galaxies. Today, we believe that there's one black hole at the center of most galaxies. But today we understand that question of which came first was actually the wrong construction, and that the mass of the central black hole and the galaxy seems to be very well correlated, which suggests that there's a connection between these two things in spite of their vastly different scales. So this project really enables enables us to look at that feedback system to understand this intimate relationship that many of our cosmological models assume. Okay, so let's start off with the first question, which is understanding what is a black hole and how do we prove the existence of black holes? Well, it might be useful to start off with what is the definition of a black hole, and it's tremendously simple. A black hole is a region of space where the pull of gravity is so intense that nothing can escape it, not even light. So we can't see it directly. And while it is an object where there is no finite size, there is an abstract size that we can associate with it. It's a scale that has been popularized by shows like Star Trek. It's called the event horizon, or more technically, it's called the Schwarzschild radius. This is the radius, which is the last radius, so the last distance that light can escape the strong gravitational field of this object. It's also an important scale in terms of understanding how black holes might come into existence. It's the scale that if you could compress a mass down to its Schwarzschild radius, and every object has a Schwarzschild radius, just depends on its mass, gravity overcomes all other known forces and forces the object to become the infinitesimally small object we understand as a black hole. Okay, so this is the radius at which gravity wins. So in a sense, the effort to prove the existence of supermassive black holes fundamentally comes down to showing that there's a large amount of mass inside a very small region, and ideally down to this scale of the Schwarzschild radius. So that's conceptually the goal. Now, the kinds of black holes that I'm interested in are the supermassive black holes, and I'm going to get to what that means in a second. And in astrophysics, we really think about two classes of black holes, and the two classes are actually wonderful demonstrations, of course, of the two ways in which we go about science. So the first class that we began to think about when Einstein was first thinking about these objects are the end states of stellar evolution. So if a star starts its life out in our galaxy with more than 30 times the mass of the sun, the conditions are such at the end of this star's life that the outer layers will explode, which is what we're looking at in this slide. So we're looking at a supernova. So the outer layers get ejected into the universe with tremendously high energy. So there's a lot of interesting and important chemistry that's happening. But from the point of view of black holes, it's what's happening at the inside of these stars that's so important. The inner scale of the star has conditions such that gravity wins. It wins over all other known forces and forces the object to become the infinitesimally small object that we know of as a black hole. And these black holes are roughly 10 times the mass of the sun. So these kinds of objects were recognized theoretically first when people were thinking about how massive stars evolve, and then later observationally confirmed. And today there's beautiful, just exquisite observational evidence from gravitational wave experiments that demonstrate the existence of these objects. Now, the kinds of black holes that I'm interested in are the supermassive black holes. And as you might imagine, they're much more massive than this first case. They're, rather than being roughly 10 times the mass of the sun, these are 1 million to 1 billion times the mass of the sun. And they exist in the center of galaxies. So that's what we're seeing here. So the scale here is vastly different. Almost every object in this slide, except the star, which has the crosshairs here, are galaxies. This is just a star within our own galaxy. So if we focus on the spiral galaxy up in the top left corner, this has roughly 100 billion stars. So unlike the one star that we were looking in the last slide, this is a very different scale. And we, from an observational perspective, started to think about supermassive black holes perhaps living at the heart of these galaxies. Now, why did we start thinking about it? There's nothing in this picture that would lend any evidence for the existence of supermassive black hole. This is a picture taken with Hubble Space Telescope. It's at wavelengths that correspond to what the optical, so what your eye detects. And it was observations in the radio wavelengths that gave rise to the idea of supermassive black holes. This is a beautiful example of a galaxy, a class of galaxies that are very energetic. And we call these active galactic nuclei because their nuclei are very active. And at these wavelengths, what we see is that there are very powerful jets of emissions emerging out of the center part of the galaxy. So you can measure the kinematic energy. So you know there's some very strong central engine driving all the activity. The scale of the galaxy with all the stars that we were looking at before is very, maybe a tenth of the scale of this outflow here. What's so important at the middle is that we see emission unlike anything produced by stars. And the interpretation here is that what we're seeing here is gas that's just outside the event horizon, the Schwarzschild radius, and falling in and feeding the black hole. So you could say that we're seeing the dining habits of a supermassive black hole. But it's this indirect argument that first led people roughly half a century ago to start thinking about the possibility of supermassive black holes. And that very quickly led to the people talking about or thinking about or positing the idea that perhaps all galaxies harbor supermassive black holes at their centers, but that in the majority of galaxies, these black holes are quiet black holes, ones that are not being actively fed. So you could say these would be black holes that are effectively on a diet. These active galactic nuclei are roughly 10% of all galaxies. So in asking this question, do supermassive black hole, is there a supermassive black hole at the center of our galaxy? We're really fundamentally asking about the possibility of the existence of supermassive black holes at all. So if we could get outside our own galaxy and look back, this is very much what our galaxy would look like. This is a zoom into that spiral galaxy that we were looking at 2 slides ago. Our sun and our solar system are roughly halfway out in our galaxy, so in one of these spiral arms. And in galaxy structure, generally, almost every quantity that you can describe becomes more extreme as you head towards the center of the galaxy. And in particular, the density of stars goes up as you head towards the center, and other physical conditions are also becoming much more extreme. So it's in this extreme environment of the center of the galaxy that we're looking for a supermassive black hole. Now, we're going to look in the center of our own galaxy for a supermassive black hole. And the advantage of doing so is that the center of our own galaxy is the closest center of a galaxy that we'll ever have to study. The next closest galaxy center is more than 100 times further away. Okay, so that is definitely the advantage of looking at our own galaxy. Now, like in life, there's usually for every pro, you usually get a con. And the challenge of looking at the center of our own galaxy is that we have to look through a tremendous amount of material to perceive the light that's coming from the center of the galaxy. So galaxies are flattened disk-like structures. So as we look towards the center, we're looking through a lot of gas and dust. And that's shown very nicely in this photograph, long exposure photograph that was taken on the side of Mauna Kea on the Big Island in Hawaii, which is actually where our telescopes are located. So you can see the band of there's a lot of white light that's coming roughly vertical in this picture, and that's the stars from our galaxy. Those are stars in our galaxy. And hopefully you can also perceive that in the middle of this band of light, there's a lack of light. And that lack of light comes from the presence of a lot of dust in the plane of the galaxy. Now, I'm from Los Angeles. I have a very good understanding from my everyday life of what it's like to have a lot of dust in the atmosphere. Dust that's roughly the size, the diameter of the wavelength you're trying to detect is very good at absorbing that kind of light. So in the optical, roughly 1 out of every 10 billion photons makes it to us. So it's basically invisible at optical wavelengths. But in contrast, at longer wavelengths in the near infrared, roughly at 1 out of every 10 photons makes it to us. So all the work that I've done has been done at infrared wavelengths. And in fact, the development of infrared detectors has been key to enabling this work. Now, the way to study or find this black hole most directly, the best direct proof that we can get is to show dynamically, in other words, by measuring the motions of stars at the center of the galaxy. So the motion of stars, these stars are moving under the gravitational influence of the black hole and all the mass that's inside their orbit. So it's just gravity. So in a sense, it's the same physics laws that drive the orbits of the planet. So each orbit tells you how much mass is enclosed within its orbit, so inside its orbit. And then the scale of the orbit tells you the scale that you've confined that mass to. So if you recall, the proof of a black hole is a tremendous amount of mass inside a small volume. So that's exactly what the measurements of stars provide you, as long as you can measure stars that are as close to the center of the galaxy as possible. And therein lies the challenge. And also my desire to get work at an institution that has the largest telescopes in the world. So roughly 30 years ago, Keck Observatory was constructed. This is a telescope that's co-owned by the University of California and Caltech, as well as a 1/6 partnership by NASA. And each telescope, there are 2 of them, obviously, in this picture, and each telescope is 10 meters in diameter. And this was a revolution in terms of mirror design at the time, because building a telescope that has a mirror diameter of 10 meters is quite a challenge. And the way this was overcome was to build, rather than a telescope with a single mirror, to build a telescope that had a mirror that was segmented. So there's 36 hexagonal segments that can be aligned to a fraction of the wavelength that we're observing at. And in fact, this was the original skepticism about this project, is that this project demands that goal had been achieved. So this work was actually the first time we got to the diffraction limit of this facility. To give you a sense of scale, what does 10 meters correspond to? This is roughly the width of a tennis court. Okay, so there are a lot. So the primary challenge of getting to the diffraction limit of these large ground-based telescopes is actually the atmosphere. So light has been traveling, the Earth's atmosphere. So light has been traveling from the center of the galaxy to us for 26,000 years. And in the last 30 microseconds hits the top of the atmosphere. And because of the turbulence in the Earth's atmosphere, that light gets completely distorted. So this is an animation, it's actual data that we collected early on in the experiment. And if there were no atmosphere, each of the 5 bright stars that are seen here would be the scale of the smallest structures that are dancing around and rock solid. So it's that turbulence and the temperature structure in the Earth's atmosphere that is creating this distorted pattern that's changing on very rapid timescales. So a lot of my work has been focused on how to overcome this distorting effect in the Earth's atmosphere. Now, there are a lot of solutions, and one of them, of course, is to get above the distorting effects of the Earth's atmosphere, and that has been the solution of Hubble Space Telescope, which has been very successful for the last 30 years, and now we've launched James Webb Space Telescope. But these telescopes, both Hubble and even James Webb, are smaller than the telescopes that we have on the ground. So if we can figure out how to correct for the Earth's atmosphere, we can get to smaller resolution, angular resolution, your ability to see fine detail with ground-based telescopes. And to put a finer point on this, while the resolution goes as 1 over your diameter, the power of these techniques for what I'm trying to do goes as the diameter to the 4th power. So it's a huge advantage to get to the diffraction limit of these really large telescopes. This is an animation that shows the success of these techniques, or what you gain from these techniques. So the 5 bright stars that we were looking at, what's called the speckle pattern, are shown here. If you take a long exposure, it just blurs your resolution of the objects you're trying to detect. Now, we think that the black hole is located at the center of the box here. So you can see that without these high resolution imaging techniques, you can't even resolve these stars, never mind track their motions. Now, the way we've corrected for the Earth's atmosphere has changed a tremendous amount over the last 2 decades. So while this experiment, which is focused on the orbits of stars, you gain a lot of power just through the passage of time once you've been successful at imaging them. There's been a multiplexing of scientific benefit because of the tremendous technological advancements that we've made in the last 2 decades in these techniques. So the early techniques were actually quite simple. They were what I would call hardware simple, software complex. So the hardware, the goal was just to take images that were short enough to keep up with the atmospheric changes. And what was necessary was just to change the optics of existing instruments such that the pixel scale was small enough to measure these effects. So from a hardware perspective, this was quite simple. And then it became a software problem of deconvolution, of understanding what the atmosphere is doing versus what your underlying function is. So on the left is just a sequence that we were looking at before. And on the right, what I'm about to show you is just the central region, which would have been just blurred out, but we've actually successfully seen these images. So this is just one image once a year. And you don't need a computer to tell you that there's already something incredibly interesting. You can probably find my favorite star in the galaxy. Its name is SO2, and you can see it moving around here. So you just have to recall that this is an experiment that people didn't think would be technically successful, nor would we actually be able to measure the motions should the imaging piece be successful. So this, I have to say, gives me a tremendous pleasure to see these old images. Now, those were the early days, the first decade of this work. So 1995 to roughly 2005. But all along the whole time, there was a parallel development in a separate approach. And this is an approach that had tremendous benefit from the declassification of a technique from the military, because of course the military also cares about looking up and down through the Earth's atmosphere. This is the technique of adaptive optics. This animation shows conceptually very nicely how this works. There are a couple of miracles that happen, like the dome of the telescope goes away. But we're going to see 2 depictions of light. First, it's going to be the beam of light, which shows the travel path. So the light comes in, bounces off the primary mirror. So that's for Keck, that would be the 10-meter diameter. And then in this design, the adaptive optic system is behind the primary mirror. So we're going to look at the key components of this adaptive optic system. And we're going to go from looking at the beam to wavefronts. And so here comes the beam, and it's going to bounce off the key element, which is here on the top right. This is your deformable mirror. So this is a mirror that can take the opposite shape, the conjugate shape, to what your atmosphere has imposed on your wavefront. So the simplistic way I like to talk about this is, if you think of the atmosphere as a circus funhouse mirror, this deformable mirror is the second mirror that has the opposite shape to make your wavefront look flat again. So we have things that look like Pringles potato chips becoming, hopefully, once we do this wavefront sensing, and are successful at flattening the wavefront. So the key is making a deformable mirror that that can be relatively small, have the amplitude, and then a system that can put the correct offsets on quickly enough. All right, so that's the key behind adaptive optics. To do this, you actually have to look at something that tells you how to reconfigure your deformable mirror. And in our case, what we've used is lasers. And in fact, this has been tremendously important to the development of the use of adaptive optics in astronomy and astrophysics. Without the use of lasers, only 1% of the sky has a bright enough star that can be used to make these, to understand what corrections need to be made. But with a laser, you can create an artificial star anywhere in the sky and make these corrections. This actually works simply because of a fluke of nature. A fluke of nature, which comes from meteorites. So the meteorites that come to Earth, or meteors, deposit a layer of sodium atoms that get trapped up at 90 kilometers. And we shine a sodium laser up to that layer and stimulate those sodium atoms to shine, and then sense those the return to make our adaptive optics system perform well. This is a night that we had two separate adaptive optics systems, both working on observations at the center of the galaxy. So it's like two giant laser pointers. It's not the beam, which you can see in a long exposure, is not the important part, but rather the light that gets stimulated up at the top. Okay, so having done this, we can actually see these stars. And we can track how they move. So this is now a fourth of the real estate of the smaller scale that we were looking at before. And you can see SO2 has made tremendous progress. With the advent of adaptive optics, you can both see fainter stars, which you can see in this animation, because imaging data, once imaging data is achieved, these stars are tracked with or depicted in this animation as being trailed by a dotted line. So sometimes stars appear, and that's just because we're going so much fainter with the adaptive optics technology. But the equally, if not more important aspect of adaptive optics is that now for the first time we can take spectroscopic measurements, which gives us the motion of these stars along the line of sight through Doppler measurements, so looking at for wavelength shifts. Okay, and then once that happens, stars are trailed by a solid line. So you can easily see, I think, in this animation why SO2 becomes the most important star, because you have a complete orbit, both from the imaging data, which gives you the 2 dimensions of motion, and spectroscopy, which gives you the missing 3rd dimension. All right, so what does SO2 do? What has SO2 done for us? At the beginning of this work, we knew that there was 4 million times the mass of the sun, thanks to earlier work, but that inside this region, that it's enormous, so big that no one could get near the claim that there was a supermassive black hole. And what this work has done we've shown that now this 4 million times the mass of the sun is in a volume that's a factor of 10 million times smaller. And that has moved the case for a supermassive black hole from a possibility to a certainty. To give you another sense of scale, this 4 million times the mass of the sun is now confined to a scale that corresponds to the scale of our solar system, where there's only one sun. So there's 4 million suns inside this region. All right, so today, this has provided us with the strongest evidence to date for the existence of a supermassive black hole by increasing the evidence by a factor of 10 million. So this is not just a small change, but a transformative change in our ability to say that there really is a supermassive black hole, not only at the center of our galaxy, but that these things really do exist in the universe. So today, going forward, the excitement is no longer about proving the existence of a supermassive black hole, but rather, but for understanding them. This is just to remind me to say this is the work that was recognized with the Nobel Prize. And while COVID was in play, there was no in-person ceremony, but this is a ceremony from the Crawford Prize, where two teams were recognized. So I really wanted to recognize that in the Nobel Prize, there were two teams that were recognized. And I really do believe that there's so much value in having two teams pursuing these difficult experiments, because there's nothing like competition for keeping you on your toes. I think that both teams think independently and therefore allow us to get to a more effective techniques at the end of the day. So there's true benefit for competition, or diversity of thought is another way of saying that. All right, so today the excitement is really about understanding black holes, both from their physical properties as well as their astrophysical role. And let me maybe share with you some of the excitement in this arena through this three-dimensional animation. What I love about this aspect of the work is that almost every prediction that we could make for what we should see at the center of the galaxy has been inconsistent with the observations. And there are three stories that this animation highlights. The first of which is highlighted by the blue-green stars. These are the young stars. In the environment of a supermassive black hole, there are very strong tidal forces, which tend to pull clouds of gas and dust apart. And that's the exact opposite action that you need to get star formation to occur. You need clouds of gas and dust to collapse. So the anticipation, and in fact, some of the early arguments against the existence of a supermassive black hole was that you just should not see young stars in this region. And yet, those are the blue-green stars. That's the dominant kind of star, part of the population that we actually see in this region. And this animation pulls back to much larger scales than I was focusing on in the first part of the talk. And you might notice that as this animation pulls back, that you see a co-alignment of many of the orbits. And so there's been an important hint from measuring orbits at larger distances, which are much longer. You see this co-alignment, which suggests that these young stars formed very much like the planets from it's like a scaled up planetary system, that there was probably a pre-existing accretion disk around the central black hole from which these stars formed. In other words, it provide much higher densities, which could overcome the tidal forces from the supermassive black hole. This also suggests that when this disk was around, our galaxy probably looked more like an active galactic nuclei in this recent past, because there would have been plenty of material that could have fed the central black hole. Okay, so that's a whole line of work that is that continues to be pursued in terms of the interconnectivity between star formation and the feeding of the black hole. A second surprise came from the story around the old stars. The prediction for the old stars, which are the orange stars, is that there should be plenty of them. And in fact, through what's known as dynamical friction, there should be intense concentration of old stars around these black holes. And that's that prediction has been used to infer the presence of black holes in other galaxies by looking at the concentration of light that's would be expected from the old stars around a supermassive black hole. And yet in our own galaxy, where we see clear evidence, these old stars seem to be missing. There are very few old stars, in contrast to this enhanced density of old stars. So there's a question about where the old stars are. And of course, it undermines some of our thinking about techniques that we're allowed to use in other galaxies. That's mystery number 2. And the third mystery, pardon me, that I want to highlight are the magenta objects. These are objects that we are seeing or detecting the tidal interactions with the central supermassive black hole. So you actually see spatially resolved these objects getting pulled apart as they make their closest approach. And that was unexpected at these distances. So to invoke this or to cause this to happen, you would need objects that are 100 times larger than anything that was predicted. And so there's a whole new line of thinking that's been introduced here about what could create these giant objects. And my favorite idea about this is that these were binary stars that were forced to merge through the action of the black hole. And when they merge, stars become puffed out. It's almost like they become young star early, even earlier than these blue-green stars. And that is providing, I think, important insight into how gravitational wave mergers might be driven by central black holes. So that's a nice connection to another field. In light of time, I think I'm going to skip this last piece and drive us to home with the last technical remark. Today, we use an adaptive optics system that uses only one laser. And while that's very powerful, there's also an important limitation because of the finite height of the sodium layer. And to overcome that, we're developing a new adaptive optics system for Keck, where we're going to use multiple lasers to effectively do a tomographic map of the atmosphere to do much better imaging. In other words, to correct a higher fraction of the distortion. Today with Keck, we actually only can correct about 30% of the turbulence with a single laser. And that fraction decreases as you go to larger telescopes. So as we're working on the development of the 30-meter telescope, we understand that it is imperative that we go to this multiple laser system. And that will be important because, in fact, today we only see a tip of the iceberg with these stars that we do see. The density of stars is so high that source confusion really limits us. So this shows a quick animation of the progress that should be made with advancing our AO on the current telescope and then enabling us to get to the next generation of telescope, where we'll hopefully go from seeing the few bright exotica to the much more mainstream but fainter stars. So to conclude, if nothing else, I've convinced you that we have a supermassive black hole, and this is a wonderful example of technology-enabled discovery. Thanks for your attention.
So it's a really exciting talk. So we have time now, a couple of questions for Dr. Ghez. Any question from the audience? And August, you might, I don't know how your system, you let people ask questions or you look at the chat.
Yes, I can do both. And there was already one question, but she had answered that question by the end. The question was, what algorithm is used to get rid of the atmospheric distortion? And I think you answered that at the end, and they said, yes, you did. Are there any other questions? You're welcome to put them in the chat, and our panelists are all of our guest speakers, so you're welcome to unmute yourself and ask questions if you would like.
Yeah, I have a quick question. Dr. Ghez, you mentioned that people use adaptive optics thanks to just a fluke, that there's those sodium atom put by million. Those atoms of sodium, do they stay there forever for us to use it, or they will be diluted, or they will be lost in,
Well, it's actually, they get replenished. So if you think about meteor showers that come through, that's the resupply of the sodium layer. So in fact, there is a season that is connected to those meteor showers.
Oh, okay. So they get to replenish with those. Oh, wonderful. Yeah. So that's amazing. So it's amazing that we have that. Otherwise, it's very hard to use adaptive optics without a reference.
Yeah, I mean, there are other tricks in terms of how you might stimulate to create the artificial star, but this so far has been the most successful technique.
Yeah, And also another question, you mentioned that the adaptive optics of the telescope work better than, you know, the big telescope like the Hubble and Webb, but with the Webb telescope, which they spend so much money, do you think that you might get some additional data?
Oh yeah, so I should have, thank you for asking that. So all these telescopes have complementary strengths. So one of the things to keep in mind with adaptive optics is that while you can get diffraction limited or near diffraction limited performance where the laser is, that performance drops off quite rapidly as you move away from your artificial star. So that means that you have limited fields of view. So at the center of the galaxy, where you have a tremendous amount to look at over a small region, the lack of a big field of view is not such a disadvantage. James Webb, which is a 6-meter telescope. So keep in mind 10 meters or 30 meters versus 6, and then you have to take this to the 4th power to do the comparison, is very powerful, and it gives you much larger fields of view than anything that can be achieved with adaptive optics. So today we actually have a number of programs with both Hubble Space Telescope and James Webb, where those 2 telescopes are used to help us understand the larger context for what's happening around the black hole compared to everything that I'm showing you here, which is a very zoomed in scale and focuses on the scale and for which orbits are possible.
Great, thank you. Any question, August, from the audience?
Yes, we have another one here that says, while having a wide view of focus, isn't the resolution affected?
So for adaptive optics, the resolution is definitely affected over your field of view. So you can think of it as a blurring function that goes from on axis where your laser is pointed. So we point our laser at the location of the black hole, and then you pay a fall off price as you move away from the laser. All our instrumentation at Keck, the field of view is within the performance of this AO system, I mean, by design. But with Hubble and James Webb, the pixel scales are bigger because your telescope is smaller. So your resolution is poorer, but it's constant. So it's a trade. So some problems are going to be much better solved with the larger field of view, and you don't care so much about having the lower resolution. So if you want to do the orbits, you need the resolution, and that's why this is such a perfect problem for adaptive optics. The resolution is the driving factor rather than the field of view.
Okay.
Any more questions?
They're starting to come in now.
Yeah. Go ahead, August.
There's another one here that says, how fast do you have to update the deformable mirror to keep up with the fluctuations?
So the corrections are roughly 1,000 times a second, and that's what works at 2 microns. So the other thing that might be of interest to this audience is that the coherence timescale and the coherence length of the atmosphere scales as your wavelength to roughly your observing wavelength to the 1.2 power. So in other words, all of this gets easier. The atmosphere is calmer and bigger scale at longer wavelengths. So 2 microns is a really sweet spot for the kind of work that we're doing. And it becomes all of this, you have to operate on much faster time scales and on much smaller scales where you start to push the technical ability. So you hit two problems. The deformable mirror has to be able to respond quickly. So you're already at 1,000 times a second. And it's actually your computational feedback. You have to be able to do the calculations quickly enough to then move your hardware around. So there's some interesting technical challenges associated with driving this to shorter wavelengths, which is equivalent also to operating at least in terms of the length scale on the larger telescopes.
We have another question. If we have time for. Oh, go
Yes,
ahead.
one more question. Yes, August.
Can you describe how the lasers are managed on the mountain, given the dark sky policy and the possibility of interfering with the observing conditions of the other telescopes?
Oh, there's actually it's called a laser control system, and it is managed by the Mauna Kea. It's a consortium of the telescopes. So in fact, it's been an interesting process to get buy-in from all the telescopes that are up on Mauna Kea. Mauna Kea is really one of the best places in the world to do astronomy and astrophysics. So you have telescopes up there from the US, the UK, Japan. I mean, there are a dozen telescopes up there, and almost all of them have signed on to this policy. So let's see, there are two parts of this, and it's evolving. Many observations don't care about the laser. There are some that do care. So this new policy of what's called first on matters. So it's basically, if you are first on, you get to do your observations. If you're not first on and somebody's doing another observations that don't care, they can give you a pass. So there's an interesting element of risk in terms of the coordination with what other people are doing. I personally have had very few collisions that have stopped the observation. I think a bigger concern in my mind is what's going to happen when Starlink goes up or becomes a bigger factor. So the other thing that has to be done when you use these lasers is you have to get approval from the FAA to shine your laser, and they tell you what the interrupts are going to be during the night. And so typically we'll have half a dozen interrupts that are a minute or two. And from my perspective, I don't really care. It shuts the laser down. You know when it's going to happen. You stop your observation and then you restart again. So it's a very minimal interruption. But if you multiply the number of things that are up there that can interrupt this, this can become I could imagine becoming a really serious interference. And of course, astronomers in general are very worried about these facilities because they reflect a lot of light. The fact that you can go out on I mean, I can see them in Los Angeles. You don't even have to go into a dark sky. These are going to create streaks, or they are creating streaks through deep, large field of view images. So there are some interesting sky policies, things that are coming up for the field of astronomy and astrophysics. Thanks for the question.
Well, August, any more questions?
That's it.
Well, again, thank you so much for an amazing, inspiring talk. Again, let's thank again Dr. Ghez, okay? So we go to another special program. So let me share my screen. Let me share the screen. For some reason, I cannot share full screen. Let me, okay.
You're good to go, Tuan.
You see my screen? Yes. So,
Yes.
you know, every year, this is in keeping with the tradition of our institute, we select a Pioneer Award in Photonics. So as you know, the Fitzpatrick Institute of Photonics established the Photonics Pioneer Award to honor distinguished researchers who have made a seminal contribution in the field of light-based science and technology. And as you know, we start from 2006 with Dr. Charles Towns, and almost every year, not almost, and the last 2 years were Dr. Donna Strickland and Dr. Ryan Weiss. And today, we are most excited to announce the 2022 Pioneer Award, and let Dr. Andrea Ghez. Dr. Ghez was born in New York City. She received a bachelor degree at the MIT and a PhD in Caltech. She's now the Lauren B. Lightman and Arthur E. Levin Professor of Astrophysics at UCLA, Los Angeles. And as she has a host of so many awards, and these are just a select special honors. So in 1994, she received the Annie Cannon Award in Astronomy. And back in 1996, the Packard Fellowship Award. The same year, the Sloan Research Fellowship Award. In 1998, she received the Newton Lacey Pierce Prize in Astronomy of the American Astronomical Society. In 1999, the Maria Goeppert Mayer Award of the American Physical Society. In 2004, the Raymond and Beverly Sackler Prize from the Tel Aviv University. In 2004, the same year, the Gold Shield Faculty Prize for Academic Excellence. In 2007, she received the Mark Aronson Memorial Lectureship. And in 2008, the MacArthur Fellowship. In 2012, she received the Crafoord Prize in Astronomy from the Royal Swedish Academy of Science. And indeed, she is the first woman to receive the Crafoord Prize in any field. In 2015, she received the Bacterian Medal of the Royal Society of the United Kingdom. In 2017, the Sven Berggren Prize of the Royal Physical Society in Sweden. In 2019, the Honorary Doctorate of Science from the University of Oxford. And of course, in 2020, the Nobel Prize in Physics. Dr. Ghez was elected to the National Academy of Science in 2004, the American Physical Society in 2012. She was also elected to the fellow of the American Physical Society in 2019 and the Legacy Fellow of the American Astronomical Society. And last but not least, Dr. Ghez is also very committed to the communication of science to general public and also inspiring young girls into science. So with all that, we are so excited to announce the 2022 Photonics Pioneer Award, Dr. Andrea Ghez. So Dr. Ghez, we are so excited.
Thank you. And thank you for the lovely, I don't know if you can see this.
Yeah. Let me stop sharing the slide. Yeah.
Let's see. Is it
Yeah, so we stop sharing the slide here.
Oh,
Being blurred. It's being blurred by your software.
yeah. We don't want that. No blurring. It's beautiful.
Wonderful.
Nice optics too.
Oh, yes.
Thank you very much.